When a customer swipes a card or initiates a digital transfer, the payment network gives the core banking system about 100 to 300 milliseconds to approve or decline. That is your entire window to detect fraud. Miss it, and the money leaves the bank. Welcome to episode 1 of Building a Real-Time Fraud Detection Engine. Today we tear down why the traditional database architectures you've been taught fail at real-time prevention and how complex event processing solves the latency problem. If you've architected around legacy banking environments, you know the standard playbook, the post-mortem. Transactions hit a relational database, you run a massive ETL batch job overnight, and the next morning an analyst queries the warehouse to find out who was robbed yesterday. Batch analytics is great for documenting losses, but useless for preventing them. An account takeover doesn't happen over days, it drains an account in minutes. So why not just use a relational or NoSQL database in real time? Because of how they operate, data is static, and you run dynamic queries against it. To catch a velocity attack, a card swiped in 3 cities in 2 minutes, your app has to continuously poll the database, scanning ever-growing tables to compute historical aggregates. At thousands of transactions a second, constant polling locks tables, crushes disk I/O, and blows past the 300 millisecond budget. Complex event processing flips this on its head. Instead of running queries against stored data, it runs moving data against stored queries. Using stream processors, like Apache Flink tied to Kafka, the event stream flows continuously in memory. You define your fraud pattern once. The engine evaluates every incoming event against that pattern. If an event doesn't match, it's instantly discarded. No polling, no disk bottleneck. Irrelevant data never accumulates. This isn't just theory. In this series, we build it. We design the event ingestion pipeline, code the sliding temporal windows that catch account takeovers in flight, and wire the engine to a high-speed cache to freeze compromised cards before the transaction clears. This is how modern enterprise architecture actually works under pressure. Next up in episode 2, we design the transaction event schema and set up our Kafka ingestion pipeline for high-velocity streams. I'll see you in the next one.